All right, welcome. Today we're going to tackle one of the most elegant and, honestly, one of the most powerful algorithms in all of machine learning, the support vector machine, or SVM. We're going to break it all the way down from a super simple real-world analogy right into a full-blown project with Python code.
So, here's the game plan for this explainer. We're going to start with the core idea behind SVMs, using a really easy-to-understand analogy. Then we'll get our hands dirty and draw our first decision boundary with a linear model. After that, we'll unlock the real power of SVMs with something called the Kernel Trick, learn how to fine-tune our model, and then, build a complete project in Python before we wrap it all up with the key takeaways.
Okay, so to really get what an SVM is all about, let's start with a simple analogy. Forget all the math and code for just a second and just picture a nightclub. You see, a lot of other algorithms, they'll just draw a line to separate two groups, say the VIPs from the general public. But an SVM is like the most meticulous, careful bouncer you've ever seen. It doesn't just want any line. It wants the biggest, widest possible gap between the two groups. This no man's land is what we call the margin, and the whole goal is to make it as wide as possible. That's what makes the model so robust. So in machine learning lingo, this line isn't just a line. We call it a hyperplane. And as you can see, its one and only goal is to create the widest street possible between the two groups. Just think about it. A wider margin means the model is way less likely to make a mistake if a new person or a new data point shows up close to the boundary. It's building in a buffer zone, which makes its decisions more confident.
And this is the most elegant part of the whole thing. The entire decision boundary, that whole hyperplane, is defined only by the data points sitting right on the edge of that margin. We call these the support vectors. They're the ones literally holding up the velvet rope. You could get rid of every other data point, and that boundary wouldn't move an inch. This is what makes SVM so memory efficient. They only have to care about these few critical points.
All right, enough with the analogies. Let's translate this idea of a maximum margin bouncer into some actual code. We're going to start with the simplest case there is, a linear SVM, where our data can be split by a nice, simple, straight line. First things first, let's get our tools ready. We'll import NumPy and Pandas, which are our go-tos for number crunching and data handling. Then, from scikit-learn, our machine learning workhorse, we'll grab a bunch of things, including the famous iris dataset. Now, if you haven't seen it before, this dataset is just a collection of measurements for 3 different species of iris flowers. Our goal is going to be to train a model that can predict the flower species just based on these measurements. Okay, now for our very first model. Just to make things easy to see, we'll start by using only 2 features. First, we split our data into a training set and a testing set, one to teach the model, one to grade it. Next, and this is absolutely critical for SVMs, we scale the data. SVMs work by measuring distances, right? So if one feature is on a way bigger scale than another, it's just going to dominate the whole process. Standard Scaler fixes that. Finally, we create our SVM model, we call it SVC, and we specifically tell it to use a linear kernel. Then we just call .fit to train it on our scaled data. And check this out. After our model is done training, we can actually look inside and see that it found 64 support vectors. What does that mean? It means that out of all the training data we threw at it, only these 64 points were actually needed to define the decision boundaries. We could literally delete all the other points, and our classifier would be exactly the same. Pretty cool, right?
Okay, so that was great for our nice, clean, linearly separable data. But let's be real, the world is messy. So what happens when your data points are all tangled up, and a straight line just won't get the job done?
I mean, look at this. This is a classic nonlinear problem. You've got one class of dots stuck right inside the other. You can try to draw a line wherever you want, but you are never going to cleanly separate the inner circle from the outer ring. This is where linear models just throw their hands up and quit. But it's also where SVMs really start to show off. So how do we solve this?
This is the absolute genius of the kernel trick. Instead of trying to draw some crazy curvy line in 2 dimensions, the SVM uses a mathematical trick to project the data into a higher dimension. That impossible 2D circle, it suddenly becomes a simple 3D bowl. And now a simple flat plane, our hyperplane, can just slice right through it, perfectly separating the 2 classes. It finds a simple solution to a complex problem just by changing its perspective. It's incredible.
And the best part? In the code, it's unbelievably simple. The only thing we have to change is that kernel parameter. Instead of linear, we use RBF, which stands for radial basis function. It's the most popular kernel by far, and it's fantastic at handling these complex cloud-like data patterns. Just that one little change unlocks all of this nonlinear power.
So we've got our linear and our RBF kernels. But to really become an SVM master, we need to understand the two most important dials we can turn to fine-tune its performance. These are the hyperparameters C and gamma. Let's go back to our bouncer. Think of the C parameter as the bouncer's strictness level. A low C is a relaxed bouncer. It prefers a wide, smooth margin, even if that means a few training points end up on the wrong side of the rope. A high C is a total perfectionist. It will make the margin as narrow as it needs to be to classify every single training point correctly. The risk? It might start fitting to the noise in the data, what we call overfitting.
Now, for our RBF kernel, we also have this gamma parameter. You can think of gamma as the sphere of influence for a single data point. A low gamma means each point has a far-reaching influence, which leads to a smoother, more general boundary. A high gamma, on the other hand, means the influence is very localized and close by, which can cause the boundary to get really complex and wiggle around individual points, again risking overfitting.
Okay, time to bring it all home. We get the intuition, we've seen linear and nonlinear kernels, and we know about our tuning knobs. Now, let's run a complete project, from loading the data all the way to evaluating our final awesome model.
So here's our game plan, which is pretty much a blueprint for tons of machine learning projects. We're going to load the data, split it, scale it, and then train our model. This time, we're going straight for the powerful RBF kernel. But we're not stopping there. We'll then use our trained model to make predictions on data it's never seen before. And finally, we'll score it to see how well it did. And this time, we're using all 4 features from the data set to give our model the best possible chance to succeed.
And here's the code that puts it all together. Now pay close attention to that scaling step. We use fit transform on the training data. That tells the scaler to learn the properties of our training data and then apply the scaling. But for the test data, we only use transform. This is so important. We're applying the same transformation we learned from the training set. If we were to fit on the test data too, our model would get a sneak peek at the test set's distribution, which is a form of cheating we call data leakage. It leads to results that look way too good to be true. After all that, we just call .predict on our scaled test data to get our final predictions.
And the results are in. A perfect score. Our SVM got 100% accuracy on the test set. But let's dig into this report. Precision asks, of all the times we predicted a certain flower, how often were we right? Recall asks, of all the actual flowers of that type, how many did we find? And the F1 score is just a nice blend of the two. Getting a perfect 1.00 across the board tells us our model isn't just accurate overall, it's flawlessly identifying each and every type of flower.
So we've seen how SVM works, and we know it can be incredibly good. But the final and maybe most important question is, when should you actually choose it for your own project?
So when do you pull an SVM out of your toolkit? Well, they are a fantastic choice for problems that are complex but not absolutely massive. They really shine in high-dimensional spaces. Think about classifying text, where every single unique word can be its own feature. Their main weakness is that they can get pretty slow as your data set gets huge, so they're not always the best for big data. And you do have to be ready to experiment a little to find the best kernel and those C and gamma values for your specific problem. So to wrap all this up, let's just think a little bigger for a second. The core idea of the SVM, not just finding any boundary, but finding the one that creates the most breathing room, is such a powerful principle for making robust decisions. This idea of maximizing the margin for safety and for confidence, that applies to so much more than just machine learning. So I'll leave you with this question to chew on. Where else in your own work, or even your life, could you apply this principle of maximizing the margin? Thanks so much for joining this explainer.
Like and subscribe for SimplfyTech, explaining one concept at a time, simplifying the technology and AI.